All right, so let's pick up where we left off with our discussion of Chapter 9, examples from Chapter 9, and we're going to turn our attention now to gauging, or determining the size and type format of the gauges that are required for positional tolerance, or actually for composite positional tolerance. So let's start with looking at just a regular positional tolerance. Okay, so we have this plate. It has like a rectangular part that sticks up here, but it's a single plate. We have two sets of holes. We have 4 holes here and 4 holes here. These holes are smaller, diameter 196, and these holes are larger, diameter 232. Okay. There's a positional tolerance with the 4 larger holes here, diameter 021 tolerance zone at MMC relative to datum's primary A, secondary B, tertiary C, ABC. And then we have a positional tolerance on the smaller 4 holes, diameter 021. Same number, but that doesn't matter. Diameter 021 at MMC relative to A, B, and C. So how many gauges do we need to determine or to check the accuracy of these 8 holes? Okay. Well, that question is based on how many different datum reference frames we have. Okay. So remember, when we have a datum reference frame that has the same number, ABC, in the same order, A primary, B secondary, C tertiary, A, B, C, with the same material modifiers. And here we're talking not about that material modifier, but material modifiers in the datum reference frame. And in this case, we have no material modifiers, and we also have no material modifiers down here. So that means we have one gauge. Okay, same datum feature references in both feature control frames, so we have one gauge that we're going to be using to check the accuracy of these 8 holes. Okay, and the gauge is going to look like this. Now, there we go. We can see all of that in there. So the gauge is the outline of the part is in blue. But the gauge is what we see in the dark black outline. Okay, so we have a datum feature A simulator, we have a datum feature B simulator, and we have a datum feature C simulator. So let's go back to this. So A is this bottom surface, B is this surface here on the left, and C is perpendicular to both of those on the bottom. All right, so that's how we have A, B, and C. Okay, the size of the pin for the 4 larger holes is going to be based on their virtual condition. Okay, so here, let's calculate the virtual condition for this. So the virtual condition for the upper pins is going to be the MMC size of the hole, right, which is 0.231, right, minimum hole, minus, because this is a hole, minus 021, 0.021 equals 0.210. Okay, so the virtual condition is 0.210, and there we have right there 0.210. Okay, there's the equation that I just did. So we have pins, 4 pins, 1, 2, 3, 4, right there, that have a diameter of 0.210. And then we have 4 pins down here, and again, we'll calculate the virtual condition. The virtual condition here is going to be the minimum hole size, 0.195, minus 0.021 equals 0.174. Okay, and here we have, again, virtual condition size of 0.174. So we have 4 pins here of a diameter of 0.174. Now, you can imagine that if we have this configuration, this gauge, right? We have a flat surface on the bottom. We have a wall here, and we have a wall here, right? And then we have 4 pins sticking up with a diameter of 210, and 4 pins here sticking up with a diameter of 174. And then our job to check to see whether this is a good part is we take it and we try to place it down on top of those 8 pins on the bottom surface against B and over against C. And if we can get that plate to be in there, then it's a good plate. Okay? We do not need a second gauge. Why? Because we have one datum reference frame here and the same datum reference frame here. All right? So we don't need separate gauges. Now that is for a single segment positional tolerance. Single segment positional tolerance. Now, what if we have a composite positional tolerance? Okay, so let's look at this example now. Okay? So we have composite positional tolerance, 021, same 021, 232 holes, right? But now we have a bottom segment, 0.011 diameter at MMC relative to A. All right. And then down here, again, we have ABC for the upper one and A for the lower one. Okay. Now, as it says right here, the upper segment here, this has a simultaneous requirement. What that means is that we check together. So we're going to check this and this at the same time with a single gauge. Okay? Because, again, I don't want to, make you assume things, but because ABC, same order, same material modifiers. ABC, same order, same material modifiers. Okay? Now, what about the lower segment? All right? The lower segments are always separate requirements. So they require separate gauges. Okay? So we need, we need one gauge for the upper segment. And we need one gauge for, and I'm going to call this, we'll call this A, and one gauge for B, and this is B. All right, so we're going to need a total of 3 gauges. Okay, one gauge for the upper segment simultaneously, one gauge for this, and then one gauge for this. So that's a total of 3 gauges. The virtual conditions, the calculation is still going to be the same, but now we're going to have, in fact, 4 virtual conditions, right? Let's do the virtual condition here. Virtual condition is equal to 0.232 minus 1, minus 0.021 equals 0.210. Virtual condition for A equals 0.231, right? That number doesn't change, minus 0.011 equals 0.220. And here we have the virtual condition for this one. Virtual condition is equal to 0.195, again 196 minus 1, minus 0.021 equals 0.174, right? Same number as we had on the last one. And the virtual condition for B is equal to 0.195, again that number doesn't change, minus 0.009 equals 0.186. Okay, so the gauging then will look something like this. we would have the, actually, let's get this. We would have this would be this would be one of the gauges. All right, forget about this part right here. This would be the gauge for both upper segments simultaneously, right? And notice the virtual condition sizes of the pins are the same, 210 and 174. But then we have a second gauge that's going to look like this, right? And let me remind you here, virtual condition for A is 231 minus 0.011 equals 220. Pins here, diameter 220. But notice nothing here. We only have 4 pins here because we're only doing these 4. All right. Also notice, because this is only repeating the primary datum, we don't have B and we don't have C. So guess what this gauge has? This gauge does not have a B datum simulator or a C datum simulator. The only thing it has are pins that are perpendicular to A. So the pins must be perpendicular to A. So this is gauge number 2. Gauge number 2. Gauge number 3 is here. Gauge number 3. And what does gauge number 3 correspond to? Gauge number 3 corresponds to this segment right here and these 4 holes. So the virtual condition here is 0.186, and the virtual condition here, you can see the pins are 186 in diameter. Notice that we only have 4 pins here, because we are not checking these 4 pins. And notice also that the only constraint that we have is we have perpendicular to A, we don't have any B, we don't have any datum simulator for C, and we have constraints on the dimensions locating the features relative to each other. Okay? So remember, for a composite positional tolerance, you're going to have one gauge for the upper segment. One gauge for the upper. You're going to have a separate gauge for each lower segment. So a separate gauge here and a separate gauge here. So in this example, we would have 3 total gauges. One for the upper, gauge number 2 for that one, gauge number 3 for this lower one. Okay? Now, we can change that if we need to by adding this note. Okay? So if we add this note right here, this note, simrect, means simultaneous requirement. And it means that these 2 lower segments are checked together with a single gauge. So in this case, we will have gauge number 1 for the upper segment. Upper segments together. Let me put a 1 there. Number 1 gauge. Upper segments together. We'll have a number 2 gauge. Lower segments together. So this and this together. All right, so what does that look like? Well, the upper segment, again, is the same as we had before. This is the gauge for the upper segment, we have an A, we have a B, we have a C, and we have 8 pins with the virtual condition sizes dictating the size of the pins. Okay? So that's gauge number 1. Gauge number 2 is going to be the lower segments. And let's do before I bring that in, let's just do the calculations here. The virtual condition for this one is going to be 0.231, right? 232 minus 1 minus 0.011 equals 0.220. And virtual condition, we'll call this A again, A and B, equals 196 minus 1, 0.195 minus 0.009 equals 0.186. Those are our virtual condition sizes. And so here is the second gauge of the lower segments together. Okay, so here's our 220 pins, 4 of them. Here's our 186 pins, 4 of them. They're together on the same plate. Notice that we repeated A here and we repeated A here. So that means that we need to have these pins perpendicular to datum simulator A. But we do not have B and we do not have C because we don't have B and C and we don't have B and C here. Okay. So this would be the second gauge. All 8 pins at their correct virtual condition sizes in their correct locations and their correct orientations. Okay. All right. So I think right now what would be good is to work through a couple of examples of this. Okay. And we'll do that in the next video.